All right. So circummotion and gravitation chapter. This is the first class for the worksheet solution discussion. In the theory practical part, we still have the uh, we have a couple of things left for the theoretical class. We have the graphs relevant to the gravitational potential and also for gravitational field strength left, which I am not showing you in today's class, but there are certain calculations that is required to be shown for the satellite motion, which I'm going to show you first, and then we'll continue with the discussion for this chapter. আচ্ছা, এখানে ইম্পর্টেন্ট বিটটা হচ্ছে আচ্ছা, for the satellite motion the parts are very simple. Let me just show you a couple of the drawings. Let's say this is a planet. Assume this is Earth. I think let's say this is Earth. We are not drawn to scale. Let's say the radius of the Earth in this case is r, and we are going to set up a satellite which is let's say preliminary on the Earth surface somewhere over here, and then we're going to send it off into the orbit. First, we're going to discuss how the mathematics of the satellite is going to be in the orbit. Then we're going to talk about how can we send the satellite out in the orbit, the whole rocket propulsion and everything. So essentially, whenever we're going to set a satellite into the orbit, if I choose a different color, maybe let's say sky blue, slightly blue, not slightly blue. So let's say if this is the orbit of the satellite, and the satellite is, let's say, h distance above the Earth's surface, having a circular orbit as well. The way the satellite is going to have a uniform stable orbit is only if it is maintaining a certain linear velocity that is tangent with its orbit, such that the amount of centripetal acceleration that it requires to maintain the circular orbit. Try to follow these words. I'm going to say it again. The amount of centripetal acceleration that is going to require to maintain the circular orbit should be exactly same as the amount of gravitational acceleration that it experiences over here, which means the pool of gravitational force should be perfectly used or entirely used to maintain the circular motion. So all of the gravitational force that exists between the planet Earth and the satellite, let's say the satellite has a mass of small m, Earth has a mass of capital M, that gravitational pool should be entirely used to be used as centripetal force. So the formula that you can write is that for a stable orbit, centripetal force should be equals to gravitational force. And now if we equate these two equations for different variables, we can write over here m omega squared r plus h. Here r is the radius of the Earth, so which is, let's say, about this much distance, and r plus h is this whole thing, which is the orbit, which is the radius of the orbit of the satellite. Omega is the angular velocity or angular speed of the satellite. We're going to replace this in terms of time period just in the next equation. But if we write further over here, this can be written as g m divided by r plus h whole squared. So gmm is the g is the universal gravitational acceleration, m is the mass of the Earth, small m is the mass of the satellite, and r plus h is the radius distance between the two celestial bodies, distance from center to center, that is. In this case, center essentially means the center of gravity, not the geometric center. For non-uniform objects, it's very important, but for spherical objects, the center of gravity and the geometric center are always the same. So in this equation, we can very easily get rid of the m and m. So these two variables are crossing out on both sides. This gives us a preliminary information that the total mass of the satellite placed at any height from the Earth's orbit would not play any role in its orbital telemetry. So in the circular orbit that you want to set it, that is not going to be affected by the mass of the satellite. The mass of the satellite is not going to be a variable because the mass is getting crossed from both sides. What does it actually mean? It simply means that the acceleration of the satellite is what plays the vital role. Mass of the satellite does not. You can have a large satellite, you can have a small satellites, which are both placed at the same orbital radius, maybe in different planes so that they wouldn't collide with each other. We can achieve that. So how much is the mass of the satellite is not a very big deal. How far apart is it from the Earth, and how often do we want it to rotate about the Earth? These are the two key factors which is important. So in this equation, I'm gonna write far more variables just for the sake of easier calculation representation. Let me just name this variable, the radius of Earth plus the height of the satellites on the from the Earth surface. Let's name this as a new radius variable. Let's say r prime. So let's say this is the orbital radius of the satellite. I'm using r prime, or I could use r as radius of the orbital radius of the satellite. Subscript x makes a good variable. So I'm going to replace these two variables over here. If I just get rid of divide both sides by the same variable. So let me just write this over here so that you can understand. I'm going to replace the omega with the expression of time period. So I'm going to write 2 pi over time period capital T whole squared. This is replacing the omega square multiplied by the radius of the satellite, orbital radius of the satellite, equals to gm divided by orbital radius of the satellite whole squared. So this is the primary equation. If we go further and process this, we can have 4 pi square divided by t square equals to gm divided by rs cube. I'm dividing both sides with rs, so this is going on the denominator side on the right side. So that's the expression. And now I can inverse the equation and write in this format: t square equals to 4 pi square divided by gm into the radius of the satellite, orbital radius of the satellite cube. This is the defining equation for any satellite that we're going to set in the orbit around the planet, or this is applicable for natural satellite. This is also applicable for the also applicable for artificial satellite, which we in generally call normally satellites, or it is applicable also for planet, if you consider the large scale for the planet and the star around which the planet is rotating by. The key information that you have to understand from this whole equation is that 4 pi square is a constant, g is also a constant. So practically speaking, this whole thing is a constant on its by its own virtue. M in this case is the mass of the central object which is producing the gravitational field. So in this case, for my drawing here, this was considered as Earth. M is the mass of the Earth. So the large object which is producing the vastly spreading out gravitational field, that one's mass, the central object which produces the gravitational field, is what we're defining as the capital M. The small m, which eventually got out of the equation, but the object which is moving within that gravitational field, so that is affected by the gravitational field. Actually, both of them are affected by each other's gravitational field. However, this is seen to accelerate more, this is seen to accelerate less because of the difference in mass. So capital M in this case necessarily represents the larger mass or the bigger mass, which is responsible to produce the more strong gravitational field, whereas the small m is the object, small satellite, or maybe the planet. If this is a star, this can be also considered to be a planet. This is the object that is moving around within the gravitational field under the effect of the force produced by this bigger mass. So m can be said in simpler words, m is the field creating mass. That's the term we use. T is the time period, orbital time period of the orbiting mass. So how much time does it take to go around the around one full cycle? That's the capital T. So for moon, that value is about 24 hours. 24 hours or 12 hours? 12 hours. 12 hours? I forgot. What is the never mind. I'll look it. I'll look it up. Uh, no. Uh, oh, sorry. The time period of moon is about only 27.32 days. That's how we define mm, uh, lunar lunar month. So the moon goes around the earth in about 27.32 days. So that's a really large amount of orbital duration. The reason we see the moon go around the earth is not because of the individual motion of the moon, rather it is the orbital speed of the earth which causes us to observe as if the moon is moving in the sky. So the moon moves around the earth pretty slowly. So it takes about 1 month to go around its entire orbit, one full cycle. However, within this time, the earth actually rotates on its own axis, 27.32 times. So we see the moon go around the earth about 27.32 days, or there may be a difference of one or minus. Uh, Here it says that the spherical month, the sidereal month of the it is the time it takes to make one complete orbit around Earth, which respect to the fixed stars. It is about 27.32 days. The Sidonic month is the time it takes the moon to reach the same visual phase. This varies notably throughout the year, but average around 29.53 days. So the lunar month is defined in two different aspects. We don't have to know this stuff. This is just a Google information. But what I'm trying to show you over here is that for any or for the natural satellite of Earth, Moon has a orbital time of about 27.32 days, or for visual aspect from the Earth is about 29.53 days. However, if we go for any other artificial satellite that we want to set up in the sky, we have to choose that how often do we want that satellite to orbit around the Earth. That is a very important key factor. In most cases, not in all cases, in most cases, satellites are typically set out in the sky to orbit around the Earth in a full fraction of 24 hours. What I'm trying to mean is that if you set out a satellite, if you have a satellite that has a time period of 6 hours, it means this satellite is going to go around the Earth every 6 hour, one full cycle, which means above a single location on Earth is going to go 4 times in a 24-hour duration. If you set the orbital duration to be 8 hours, it's going to go above a single place on Earth 3 times every day. If you set it at to be, let's say, 12 hours, then it's going to go around two times. If you set it at any other fraction, you can also find out that how far would it move around a single location. The reason this type of fractional discussion is this type of fractional time durations are pretty important, because that is basically how all the weather forecasts are made by means of different scenario. If you guys if you guys ever recall that if you have seen the news, the forecast of a cyclone or a tornado that is happening above the country, maybe on Bangladesh or any other country, you would see that the images they show for the position of the cyclone, that is actually not a continuous video. It skips frame by frame. So you have the cyclone at certain duration, then it tends to what can I say? There seems to be a glitch in the video, something like that. It actually skips frame and goes into the next direction, goes in the next direction, and projecting how far it has moved over a certain duration of time, we can practically predict how fast the tornado is moving in any direction. The reason we don't have a continuous video shoot of the cyclone's top view, rather we have fixed images, is because we do not actually set up a fixedly oriented drone type of anything on top of the cyclone to have a look at the cyclone. All of these images, weather images, they are actually captured by satellites which are in the much higher above in the stratosphere level, so they are not affected by the climate or any other stuffs. But they were definitely affected by the gravitational field of the Earth. So they go above that region. Let's say the 6-hour satellite goes above that cyclone 4 times a day. The 8-hour satellite goes around that cyclone, let's say 3 times a day. And you can have multiple of these 6 and 8-hour satellites, or even a fraction of those values satellites. That's also can be achieved with accurate calculation. Why not? These satellites capture the top view image of the cyclone and sends them down to the ground receiving stations. All of those images are then sorted in chronological order. So it means that at what local time for that location, these images were taken. And then all of these images are synced one after another. So when they are played as a slideshow, then we can actually see how the cyclone is moving with all of its clouds, and it's moving from one place to another place. So that's the reason we have all those skip frame kind of video shoot. For those of you who are not getting the idea what do I mean by the word skip frame, let me just try to show you so that it might make slightly better sense. Cyclone view. Okay, so this was done by an airplane, which is a bit different. Yeah, exactly. This is the image that I'm talking about. This is how big of this video? This is 49.29. But even if I'm not getting into the video, if you just have a look at the thumbnail that we have, you can see that the cyclone is slowly moving apart. And what I need you to understand that all of the images which make the cyclone to give us this kind of a continuous story is not done at every single second. These were images taken for minutes of differences. So this is sort of like a time lapse. Do you guys understand what a time lapse is? Palawan?
Yes, sir.
Do you understand what a time lapse video is?
Yes, sir.
আচ্ছা বুঝো না কেউ আসো? In that case, I'll explain, or maybe I should explain anyway. Let me just tell you. A time-lapse video is basically you are setting up a camera towards a long duration happening, and you set the camera in automated instruction that is going to capture a single image of that happening. Let's say every 2 minutes, or every 4 minutes, or every 10 minutes, depending on how long do you want to capture and how big your memory space, and what is the resolution of the picture that you're taking. So all of these factors can contribute to how long can you shoot, or the battery life is also another factor, very important factor. So the idea of time lapse is that if you take, let's say, an image of let's say, a flower blooming up, maybe that process might take, let's say, half an hour. If you take an image of the flower blooming up, let's say every 20 seconds, then every minute you're going to have 3 shots. So within a 30-minute duration, you're going to have 90 fixed images of that flower blooming up. If you set up all of these images in a, let's say, 2-minute video, so this is gonna, we're gonna see that the flower is slowly becoming larger and the petals are slowly spreading out. That kind of a view is what we call a time-lapse video. So the satellite images can give us a time-lapse view for the weather information, so something like that. So T is a pretty important information for us to understand that how often do we want it to rotate around the Earth. And depending upon T, the R is actually becomes a defined factor. So you can see that T square is proportional to R cube. If I take the constant out of this equation, I could very easily write this as T square proportional to the orbital radius cube. This relationship, interestingly, was actually developed by astronomer, a very ancient astronomer who is called Kepler, and this proportionality was derived and proposed by scientist Kepler first. It's called Kepler's law, that the time period of stars are directly proportional. Square of time period of stars is directly proportional to the orbital radius. He made the observation of multiple different celestial bodies and came up with this proportionality on his own. Later, we actually got into the whole equational approach, and eventually this equation was developed, and it was found that Kepler's law was actually a valid observation. So that's the underlying principle for how does a satellite work. Important information one more time. For a satellite to have a stable orbit, stable circular orbit around a planet, it must be have a very specific linear speed that is tangent to its orbit, such that the required amount of centripetal force to maintain the circular orbit is entirely and exclusively provided from the gravitational pull of the planet. The gravitational pull of the planet must completely cause the satellite to undergo in circular motion. That relationship, the centripetal force is equals to gravitational force, is really, really important. If we don't have this balance, two of the things can happen. Either the satellite is going to slowly start to rotate in a smaller radius and speed up, because it's going to get closer to Earth's orbit, it's going to definitely lose GP, and that's going to convert a small portion of that energy, GP loss will be converted into kinetic energy of the planet. So it's going to slowly speed up, speed up, speed up, speed up, speed up, and eventually it can fall onto the Earth's surface, which is also quite unlikely because Earth is actually covered with atmosphere. If the satellites ever start to fall close to Earth, the faster it's going to move through the atmosphere, the more friction is going to generate by colliding with the atmospheric particles. So in most likely cases, much of the satellite is going to be burnt out before any solid particle actually falls onto the Earth's surface. That's the most likely scenario for most of the satellites. However, if there are some very heavy materials which are not going to burn out, then certain amount of fragments can actually fall onto the surface. They're going to hit the surface at a really high speed. Uh, Definitely, if it's the, it can be fatal for human beings if someone is in the path, but it's a pretty unlikely scenario. That's one scenario, that if these two forces are not equal, then either the satellite could actually fall into the closer to the Earth, or in other cases, if any of these forces are not equal, then the satellite might actually slowly start to go out of the orbit and eventually drift into the vastness of the space and eventually get loose from the planet altogether. This second scenario is basically the principle by which we can actually make interstellar travel. So if we want to move around the, if we want to leave from the Earth and eventually go out into the sky and set a planetary orbit for any moving object, we have to achieve certain amount of conditions. We have to go by some set of rules. For the upcoming part of the discussion, I'm going to show you that how the Earth's radius actually affect the value of G, and how the orbital rotation of Earth actually affects the value of G. These are the two factors which can prove to be very important for us, and I'm going to show you some examples of those for the next part. So first thing first, I can expand this page a little bit more. Yeah. The first thing is that you need to understand that for the entire duration that we have been discussing gravitational law, we have been considered the two objects which are under the effect of gravitational force to be particles, which by definition has some significant measurable mass, but they have zero volume. If that's generalization, or that's an approximation. Typically, objects are not particles. Objects have volume and they have some shape and size. Earth, by its own shape, is not perfectly a perfect sphere. It is a bit squashed in the north and the south pole, so it is a bit like orange kind of shape. পৃথিবী কমলা লেবুর ন্যায় গোল, এটা আমরা ছোটবেলায় শিখছি বাংলায়। Anyway, how so that variation of radius, which is a bit big on the near the equator region and is slightly small near the polar region, basically tells us that the gravitational pull should be a bit stronger on the pole because R is small. You should remember that the value of G is actually given by Gm by R squared. Now, this m is the mass of the Earth, which is a constant no matter where you stay on the surface of the Earth. So the value of G is actually basically dependent on the radius of the Earth at a certain location. This, I'm using the term radius because here I'm assuming that if this is the planet Earth, we're going to measure the gravitational field strength or gravitational acceleration on the surface of the Earth. So for an object that lies on the surface anywhere, so an object which is on the surface basically is r distance away from the center. Now, because of the shape difference of the Earth, near the equator region, the radius is slightly big, and near the polar regions, the radius is slightly small. That's why G has the smallest value, right, or somewhere over here on the exactly on the equator, and G has the largest value on the polar regions. These value differences can be significantly large. For example, in the in the poles, the value of G is about 9.8217 meter per second squared. You don't have to memorize these values. I just remembered them from my own personal syllabus from SC and HECs. So that's the value of G in the pole. So this is about 9.83. I'm going to give, let's say, 2s of values so that you understand. 9.83 meter per second squared. Whereas the value of G in the on the equator is about 9.78039. So I'm going to write 9.78 meter per second squared. So that's a significantly high difference. Now, if you wonder that why do we use the value of 9.81 for our calculations in all cases, since there is a significantly different variation of these two values, the reason is that for the sake of scientific calculations, this what the scientists decided by because of under a lot of practical reasons as well, which I'm not discussing right here. You don't need that. I don't know them either completely because I didn't study about it. But for practical reasons, what the scientists considered that for scientific purposes and also for regular life purposes, we're gonna have a fixed. We need to have a fixed value of G so that all calculations are synchronous. So what they decided that at 45-degree latitude, I always mess this up, so I'm gonna look it up. Then I'm gonna talk about latitude and longitude. One image should be enough for me to understand this. Okay, so horizontals are the latitudes, the verticals are the longitudes. Beautiful, I got it. So what does science say that at a 45-degree latitude, the G measured exactly at sea level, not below, not higher. The value of G measured exactly at sea level, exactly at 45-degree latitude at Earth, would be considered to be the standard value of G for all practical reasons. And that value of G is about 9.80665 meter per second squared. So in a 3SL value, this is 9.81 meter per second squared. So that's the value that we preferably use for all of our calculation. So that's one of the idea that you have to understand, that following this equation, because of the shape difference of Earth, more wide on the equator region and less wide on the polar regions, G can have a bit of a varied value. There is another factor to it. The same factor that attributes towards the variation of G is because of Earth's radiation. Because of Earth's rotation. I used the wrong word. Because of the Earth's rotation, its axial rotation, that it goes around its own axis. That rotation actually cause a significant actually cause a significant variation if you can measure it. We human beings might not actually feel it that high because our brain is accustomed to these changes to some extent, but if we want to measure them, we can actually measure them with appropriate equipment, and definitely we can calculate out the effect. Before I tell you how does the rotation of Earth actually affect affect the value of G, or in other words, our weight or the gravitational pull. Let me give a very simple example for a horizontal circle object. What example can I take? Okay, let me pick up a simple example. In the in some of the parks, amusement parks, there are many type of rides. One of these rides is actually, I think it's called the Stickman, not the Stickman, it's the Sticky Man, maybe the Sticky Man, or Fly in the Wall, something like that. I forgot the name of the ride, but the idea of the ride is like this. There is a circular platform over here, and there is a wall around the circular platform, and there is the open thing, open part, open. And this is the roof is open, and usually there is a door people can come by and they are asked to stand against the wall on the far side, not on the center. And then this whole disc shaped thing, this is actually pretty large. It's like a cylindrical room with floor at the bottom. Then the disc is started to rotate about its axis at a pretty high speed. So it slowly accelerates and accelerates and accelerates. As the room starts to accelerate, any person who is located, let me just try to draw a person with brown man. So there is a person who is getting squashed against the wall. As the room starts to spin really fast, the person is actually pushed against the wall. Now you might wonder why the person is getting pushed against the wall. The person will feel that he is being pushed against the wall. The reason is that the natural tendency of any object is to maintain its velocity. So the person's body, the mass of the person's body, is trying to maintain a linear velocity, which is not allowed because of the wall. The wall is causing the velocity of this person to change every single. Let's say at one instant it is in this direction, the next instant is in this direction, the next instant it is in this direction, then it is in this direction. So there is a continuous change of velocity direction, and to cause that change of velocity, the person is being pushed from the wall. So the person is inside the wall. The wall is pushing the person. Let me show that by maybe a blue arrow. The wall is pushing the person towards the center. And the reason why the wall is pushing the person towards the center, this is because the person is pushing the wall. The person is pushing the wall because the wall is in his path of straight velocity. The wall is in his path of straight velocity, but the wall is not allowing that straight velocity because the wall is the strong object and it is causing the person to go around in a circle. So the person is pushing against the wall, which we call the centrifugal force in some cases, and the wall is by Newton's third law is pushing on the person. These two arrows should be at the same level. I beg your pardon for my wrong drawing. The wall is pushing on the person towards the center. This is the reaction force of the wall onto the person. This is the force which the person is using as centripetal force, in this case the reaction of the wall. And this push force can be increased further higher and higher and higher as the object, as this disc shaped thing or the cylindrical wall room is actually rotated faster. I can give you some mathematics for this. Let's say if the mass of the person is m, and in that case the value of the centripetal acceleration can be given by F equals to m omega square r, m omega square into r. R in this case would be, this is necessarily the radius of this whole cylindrical room. This is the value of r. So if we slowly start to increase the speed of the rotation, then the FC will slowly get higher and higher and higher. Now you might wonder, well, the FC is getting higher, so it means the person is getting a lot of centripetal. The person is pushing against the wall a lot harder. The wall is also pushing onto the person a lot harder. So basically, the person starts to experience a very strong squishing force, as if something is pushing onto the person against the wall, although the wall is continuously moving. This sensation is essentially what we experience as a high G scenario. Typically, our body is accustomed to the gravitational acceleration of Earth, which means our senses are qualified, our senses are habituated, adjusted towards 9.81 meter per second square of acceleration on our body. The moment we start to experience a bigger acceleration, that's when we sense that as if something is pushing us or squashing us. If we start to sense less acceleration than that, then that's what we call weightlessness. Weightlessness is the scenario that we can have if a certain person takes a jump off a rooftop, or if a person is in a lift and somehow the cable breaks off, or a person takes a small jump off from the top of a boundary wall. So for the duration that the person is having somewhat of a free fall, the person is not exerting force onto a solid ground object, either the floor or any other solid object. So because the person is not exerting the force onto anything, that surface is not exerting any reaction force on the person's body, and the person does not sense their weight. The way we sense our weight is by means of the reaction force. Think about it. Every single orientation that you are in, whether you are sleeping or you are awake, you are moving or you are stationary, you are running or sleeping or doing whatever, you always experience a certain upward force from the lower part of your body. If you are standing up straight, you sense that the floor is pushing against your, what do you call the bottom of the feet, the white skin, what do you call it?
Soul বলে স্যার ওটাকে।
Huh?
Sir, soul, but spelling take two different.
Acha, soul, swelling, yes, yeah. Yeah, yes. My head was giving me delivering the word toe, but I remember the toe is only the name of the nail, the large one. So yeah, soul. So if you're standing up, then we experience that upward force against our soul. If you're sitting on a chair or something, you experience that force in your hips and in your thighs muscles. If you're lying down, you experience the entire force onto the part of the body, depending upon in which direction you're lying down. It might be lying up, facing the right, or facing left, or facing down, but you experience that force onto the lower part of your body. So we are always accustomed to getting a certain amount of force feedback from the ground in the upward direction onto our skin, and that sensation is essentially registered in our head as the effect of gravity. That's what tells us that our weight is working. At any point of time, if that force is taken away, if we are not experiencing any upward force onto our body, that is, then our brain tells us, gives us the sensation of weightlessness. That is essentially what happens whenever that is essentially what gives us the sensation of a bit of a risk. And risk is associated with adrenaline is also associated with some sort of joy and excitement. And that's essentially how pretty much every ride in a amusement park or theme park actually works. For roller coaster rides, it works. It takes us to a very high place by gaining GP of electric motors and chain mechanisms, and then it drops us from a very high height. So as we start falling, although we are strapped within the device and everything, but as we are falling along with the whole vehicle, the sensation of losing weight gives us a sense of danger and excitement, which are really overlapping type of senses. Point that I'm trying to make is that whenever, when getting back to this whole concept over here, that the person is going to experience this FC amount of force working on his body. As the disc is going to start rotating faster and faster and faster, the person will push against the wall much more strongly at a very high force, and the wall is going to also push against his body towards the center with the equal amount of force. So the person is going to get experience a very strong lateral force. It is possible that for such a strong push force, the friction that will exist between the person's body and the wall will be strong enough to balance their weight. I mean, this is the part that I want you to understand. Where does the friction come from? Let me give you a simple idea. Let's say this is a horizontal scenario. You have a piece of brick over here. If I ask you that move the piece of brick by pushing it, you might as well push it by a single finger. Possible. But then if I stand on this brick, let's say this is me standing on the brick, figure not drawn to scale, and then I ask you push the brick, you cannot definitely push it with a single finger. You might not as well be at all be able to push it. The reason is that when I'm standing over here, I'm exerting a very significantly large amount of force between the contact area of the brick and the surface. So the friction has gone very, very high. If you still want to move this, we have to push it really, really strong. That's pretty much the same thing that is happening over here. Only in this case, that is a bit, if I just rotate by right. So this is a scenario that is happening over here. The person is being pushed against the wall with his whole body, so at such a high force that the friction between the person's body right over here and the wall can go to a very high value. The way this whole ride works is that they start to spin it up at a certain speed, and beyond a certain speed, when the operators know, this floor slowly starts to detach and it starts to go down. So what the people are going to see, that up till now their feet were standing onto this floor, but now as the floor is moved away, the floor is going to move down, but the people are going to still get stuck onto the wall. They're going to get stuck onto the wall, and as long as the disc is going to keep rotating, they're going to keep remaining stuck on the wall, because at this point their weight will be perfectly balanced by the frictional force that exists between the person's body and the wall. So I have a reason to take this much time to explain this example to you, because there are mathematical and theoretical questions that many oftentimes come in your syllabus, also in other syllabus like AQA and WJC, that what is actually happening for all the forces involved for a scenario like this. Somehow the CA people really love this example, and it's actually a good example. It can take into account in a lot of relevant forces. We are talking about weight, friction, centrifugal force, and we're talking about the radius and so on and so forth. It's a good example. So the this is actually friction. So I'm going to write, let's say, small f, maybe friction represented by small, because the person, because of the weight of the person, the gravitational pull of the person would naturally try to go down, but the person is not able to go down because the friction that exists between the person and the wall is strong enough to hold the person over here. So it's something like this, that let's say you are trying to push this brick in the upward direction, whereas the weight is trying to pull this brick in the downward direction. If these two forces balance out each other's effect, then the brick is going to be stay in the same position. Acha, maybe that didn't answer your question. Let me rephrase the answer in a different way. The disk is going up, spinning, is moving, is spinning, and the person's feet are still onto this horizontal ground plate, this radial plate on the floor of this whole ride. As long as the person exert a force onto this floor, the force is going to give him an equal amount of force upwards. But try to think about it. If this person is actually stuck onto this wall with some glue, for example, or with some nails, not through their body, let's say with some straps and nails. So if the person is somehow glued to the wall, do they actually require this floor?
No,
If you
sir.
duct tape a person onto a wall, do they require a floor to stand up on? They don't, right? That's pretty much what is happening over here. The person is gaining enough frictional force because of the squashing effect onto the wall, that his weight or her weight can be perfectly balanced by means of the frictional force. So moving the floor down is not going to make them unbalanced or fall down towards the earth, because they are now getting squashed to the wall to such a high frictional force that they are stuck there. This is only achievable at a pretty significant high amount of angular speed of this whole ride, and that's the whole point of this ride, that they do this, and beyond a certain speed they move the floor down. Everyone is stuck onto the wall, and they can move, they spread out their hands and everything if they can. If they have enough muscle powers to still get their hands and feet out of the wall, they can still do that, and that gives them a sensation of slight amount of weightlessness. But in this case, the reason they feel the weightlessness, because they see visually, they see that their feet is not on the ground, but they are still pushed onto this wall. So that idea that I just told you, that as long as we experience a squashing effect on our body from the bottom upwards, we always sense our weight. In this case, the people are gonna still sense their force on behind their back, that is coming against the wall. So physical senses are still going to be there, but their visual information, the eyesight is going to tell them that apparently they are just floating. So that's a bit of exciting to some extent. I think it's quite exciting, and they run this for a couple of for some duration, maybe 1 minute or so, and then they lift up the floor once again, and then slowly slow down the ride and let the people walk out. So that's how the ride works. Now, why am I telling you this? What is the relevance of this whole example for a satellite scenario, or for the case of the weightlessness? The point that you need to understand, that as the person was actually being rotated at an increasingly oops, at an increasingly at an increasing omega angular speed of the ride, this person was getting pushed against the wall. You have to understand, this person is actually not stationary. This person is continuously going around in circles. I have drawn this person in one position because I cannot essentially draw in all the positions. You have to understand that this person is going around like লাট্টু তো না, এটা কি মানে স্যাটেলাইটের মতো কন্টিনিউয়াসলি এই ওয়ালের সাথে লেগে কিন্তু ঘুরতেছে. So he is continuously going around this circular orbit, and it's a vertical vertical axis, horizontal circular orbit. So he's going around in circles. He's not stuck there. Don't get the wrong idea. The reason I have given you this anti-clockwise arrow is to give you a vision that this ride is on motion. It is going around. So as the person is pushed against the wall with a bigger and bigger amount of force, the friction is going to slowly increase more and more. As the friction of the person slowly increases to a higher and higher value, the person is gonna have to exert less and less force by their feet onto the ground. Try to understand this thing. Let's say the person's weight is exactly 100 Newton, although not quite likely. 10 kg person is not a good idea, but for the sake of understand, let's say the person's weight is only 100 Newton. When the ride is stationary, it's not moving at all, there is no frictional force between the person and the wall. So person exerts all of the 100 Newton force onto the ground and receives 100 Newton force back from their feet in the upward direction. He senses the entire weight. Let's say the ride is now working and the person is pushed against the wall, and now friction has now increased to, let's say, to a value of 30 Newton. What does 30 Newton frictional force mean? It means naturally the person is capable to exert 30 Newton force onto the surface vertically and get that 30 Newton force compensated out of the friction between the person's body and the wall. Because he's being pushed against the wall at a very high force, you now have a significantly large force, which means when the friction force is 30 Newton, the person is not going to exert 100 Newton force onto the ground anymore. How much is he going to exert onto the ground? The remaining force, because he's getting compensated for 30 Newton from the friction. So that out of the weight, the 100 Newton weight, he now only can exert 70 Newton force downwards. So he's going to exert a smaller amount of force onto the ground, and the ground is going to give him a small amount of force in the upward direction. Hence, the whole idea of weightlessness or less weight comes in. And the faster the thing is going to start to rotate, the bigger this force is going to become bigger this force is going to become. And at one point, if the force is so high that this frictional force becomes exactly 100 Newton, that the person does not have to push any weight onto their feet onto this floor space. And that's pretty much when the idea of somewhat levitation without the support at the feet can be achieved, although the person is actually supported by the frictional force on the wall. But many people don't understand physics, so it can be somewhat magical for them. What I want of you to understand that the person is having a bit of a less weight because of the increased circular motion, because of the frictional force getting involved over here. What happens for Earth?
Sir, friction থেকে weight কে exceed করতে পারে না?
Ideally না। Ideally না, এই জন্য the maximum force the person could possibly experience vertically downwards is equal to weight. Now, the idea of friction is that if you have an object on a certain surface, you can get a value of friction that is not more than the applied force. Let's say, try to think of a regular scenario. For example, maybe when this was horizontal, let's say your laptop is sitting on your table. If the maximum friction of this between the table and the laptop is, let's say, 50 Newton, and you exert a force of 5 Newton, at that point the friction force will also be 5 Newton, perfectly compensating your applied force, right? Can you get a bigger force than 5 Newton if you are applying 5 Newton in terms of friction?
No, sir.
The friction can be more, but as long as you don't increase your applied force, you cannot get a bigger frictional force. The frictional force will perfectly match your applied force till the value of 50 Newton, because that's the limiting value of the friction between the laptop and your table. So if you start to apply a force bigger than 50 Newton, let's say if you apply 7 Newton force, then friction is going to compensate for 50 Newton of it, and 20 Newton force can give you an actual acceleration. In this case, the maximum force that the person could possibly exert onto the wall working downwards is 100 Newton only, because that's his weight. The person cannot exert more than that because this person is not being pushed or pulled by any other external forces. Weight is the only vertical force involved here. So the maximum friction that you could possibly get between the person and the wall is 100 Newton, causing them to levitate.
স্যার, তাহলে স্পিড যদি আরো বাড়াতে থাকি তখন ফ্রিকশনটা 100 নিউটন হয়ে যায়।
The moment the vertical friction and the moment the friction and the weight becomes equal, we have vertical equilibrium, which means you don't have to bother for the forces anymore. If we keep on increasing the angular velocity even stronger, the person is gonna get squashed more to the wall, and the maximum possible friction will increase. It means, let's say at a certain speed, you have exactly 100 Newton frictional force. The person is on limiting equilibrium. You speed up the ride a bit more, and maybe then the maximum frictional force becomes 120 Newton. Try to understand that. at a certain angular velocity, the maximum frictional force. So I'm talking about F max over here, that the person is being squashed with the wall to such a high force that the maximum frictional force is now, let's say, 120 Newton. At this certain value, they actually move this thing down, because not all the person might have the same amount of frictional force, because some people might be wearing silk, some people might be wearing cotton, some people might be not wearing anything. Weird situation, but not impossible. Whatever. My point is that the maximum value of friction should be somewhat more than the weight of the person. The maximum value of friction. That's the important part. And in this case, whenever your maximum friction is more than the weight, and then if you only exert the weight, the friction can uphold that value. If we start to spin the disc faster and faster, this value will increase. But the effective friction can only go as high as the actual weight of the person. That's my point. Zaib, did you get my point?
Yes, sir. আর স্যার মানে আপনি যখন রেজাল্টেন্ট ফোর্স যখন 70 নিউটন ছিল, তো এই রেজাল্টেন্ট ফোর্সে কি হচ্ছিল? কারণ ওর তো নিচে তো মুভ করছে না, অ্যাক্সেলারেশন তো নয়।
Yeah, for my example, the way I was explaining this is that when the frictional force is about 30 Newton with the wall, the person can only exert 70 Newton of force through their feet onto the floor of the ride. In that case, they were exerting 70 Newton onto the floor of the ride through their feet, and their feet was also getting 70 Newton back. So their feet was getting a bit of less upward force than they are usually used to. But that would not give them the sense of flying or weightlessness, because now they are once again squashed against their back. So the physical senses of the pressure senses of our skin that tells us the sensation of weightlessness is actually getting compensated. The only way they will have somewhat of a sense of flying or weightlessness is when this floor is actually moved all the way down a little bit, and the people actually see that they are not standing on their feet anymore. So that visual input will be sensed as the what kind of sensation of joy or something like that. The question to your answer: when the friction is 30 Newton, then the person is going to exert 70 Newton force through their feet onto the floor and get a reaction force of 70 Newton back from the floor on their feet. That's the exact answer of your question.
Thank you.
No problem. Any other question? This is a good example. So if you all indulge over here and ask me a question that you want to get answered, it would be nice. Anyone else?
স্যার
বলো।
স্যার এই যে রাইট সাইডে যে দেখাচ্ছেন না যে হরাইজন্টালি কেউ দাঁড়িয়ে আছে একটা ব্রিক বা কিছুর উপরে,
Yeah, this one.
ইয়েস স্যার। তো এখানে তো আমার ওয়েট তো আমার বডির সেন্টার থেকে কাজ করবে, আর ফ্রিকশনটা তো আমার সোল আর ব্রিকের সারফেস এই দুইটার মাঝখানে কাজ করবে, তাহলে ব্যালেন্স কেমন হবে?
Oh, in that case, you're gonna have a little bit of moment available in the situation. So good observation. Good observation. Let me draw this for you. I shouldn't draw for this example. I use this example to make sense of the friction getting increased with exert increased force. But I'm answering your question. Hold up. Let's say this is the wall of the ride, and considering this is the person, figure not down to scale just for the sake of simplicity. This is the person. This is the center of gravity of the person. The weight of the person works from here, and the frictional force works over here. So necessarily these two forces are going to produce a couple onto the person, right? If not couple, they're going to produce a clockwise moment on the person, right?
Yes, sir.
The person is definitely going to have feet. I mean, if the person was actually a spherical object, the person might be actually seen to go around in a clockwise motion, but that's not a typical thing for a regular person. What we will see that this person is going to be actually squashed over here, and their feet is going to stop that rotation. So using their feet, they're going to experience some additional vertical force, which is going to produce equal amount of anti-clockwise moment to balance out that moment scenario, so that you can have equilibrium. I mean, think about it. If you're trying to rotate this person at this scenario, because of this moment, you have to actually coil the person against their waist, right? Like a
Yes, sir.
jalopy or something. But they're not going to allow that. Do I make sense? Somewhat.
Yes, sir. You can do. Yes, sir.
That's beautiful. So this is one of the examples that is pretty interesting to discuss. And now I'm coming back to the point that how does the rotation of Earth actually affect the value of G? And why is it helpful in a certain given case for the for launching satellite into the outer space? I mean, the rotation of Earth can also be used handily or usefully for sending satellites into the sky. This is how it works. Let's say this is the Earth. Let me draw a bit elliptical. Obviously, figure not drawn to scale, so bear with me. This is the center of the Earth. This is the equatorial line, and this is somewhere around the pole. Now, for this thing, I need all of you to visualize the circular motion in a bit three-dimensional view. So let's say an object which is located over here goes around the Earth's equator, let's say in a circular orbit that looks like this. I'm showing you an ellipse because I want it to be a bit of a 3D so that you can have a bit of a 3D understanding. So do you understand what I'm trying to show over here? So the object is, Earth is rotating, and this is the circular orbit around the equator region for this object. Now, what I needed to understand that, let's say the mass of the object is m, and the pull of the Earth towards the center is, let's say, given by Fg. This Fg is equals to, let me write those variables on the top. Let's say the gravitational pull on this mass m is given by Fg, force due to gravity, g, which is given by g m by r square. Okay, I should give a capital R maybe. Yes, using a capital R actually helps. So this is the value of g. The centripetal force that the object requires to maintain the circular orbit, let's say that is given by Fc equals to m omega square r. I'm using the term omega square over here because I'm not using v square by r, because I'm going to slowly start to observe this object to move from here to towards the pole. So it's going to have different circular orbits at different heights, pretty much somewhere around the longitude and okay. Let me latitude. Yes. So if you look at this image, what I'm trying to tell you is that currently I'm considering the object to be located exactly on the equator. But if I take the object a bit higher in the latitude level, then the circle is going to be different, because Earth is still going around around its vertical axis. So the orbit is going to be this. If I take it further above, the orbit is going to be this. If I take it further above, the orbit is going to be this. So you're going to slowly have smaller circumference orbit, and that will definitely affect your linear speed v. But your angular speed omega would pretty much remain the same. The reason is that irrespective of the position of the object, this object is still going around the entire circle in 24 hours. Whether you place the object over here, it is 1 full day is 24 hours. If you place it over here, 1 full day is still 24 hours. 1 full day is still 24 hours. So having the variable omega involved in the equation helps us to get rid of the possible change of linear velocity, because we can have the omega to be constant for all the positions. That's why I'm preferring to write this Fc expression in m omega square r rather than not in m v square by r, because if I did write in v square by r, I would have to I'd have to take into account the change of v for my upcoming calculations as well. Do you understand my point here? Why omega and why not v for this exact expression? Bolaban.
Yes, sir.
জি স্যার।
আচ্ছা, so for this expression fc is only dependent on r. For this case the fg is also dependent on r apparently. And what I need you to understand that fg is the pulling force that the m object experiences because of the gravitational force. Try to understand my words very carefully. Let's say at any point the, let's say on the equator, the gravitational pull on the object is, let's say, 100 newton. 100 newton. Newton, sorry, n, not n, Newton. To maintain an orbit of time period 24 hours around the whole equator line, let's say the object requires a centripetal force because it is undergoing a change of velocity because of the change of direction. So it requires a centripetal force to maintain that thing. Let's say the required centripetal force at the equator region is only 5 Newton. Now, I want you to understand this thing. By virtue of gravitational force, this object on the surface of Earth has 100 Newton force available to itself, working towards the center of Earth. Out of this 100 Newton force, it needs to spend, or it needs to utilize 5 Newton force continuously to maintain its circular motion. So it has a 100 Newton force because of gravitational pull, but to maintain circular motion, it has to always use 5 Newton force. So how much force is left? 95 Newton force. This object is going to push on the Earth's surface using that 95 Newton force, not with all the 100 Newton force, because out of this 100 Newton force, 5 Newton force is always continuously being used to maintain the circular motion. So you are using a portion of the available force for circular motion. Whatever you have remaining, you are exerting it onto the Earth's surface. So in this case, the force onto the Earth, or I can say the weight, is gonna be 100 minus 5, which is equals to 95 Newton. Do you understand my point? Do you understand the idea of that 5 Newton is being used continuously? Does this idea make sense? Try to think about it. The Earth is on, the object is on the equator. So as the Earth is rotating around its axis, the object is continuously rotating in a circular orbit. Any circular motion will always require a centripetal force. The source of that force for this case is the gravitational pull between the object and the Earth. So it's going to use a fraction of that available force to maintain that circular orbit. And then the remaining thing is being pushed onto the Earth as a active force, which in turn gives us the weight. So if we now actually place, if we now take the object a little bit high up and place an actual weight machine, mass balance underneath this object, we're going to measure this to be 95 Newton. Whereas if we take the object exactly on the pole, you have to understand this part. What is the radius of circular orbit at the pole? If you bring the object from here all the way up at pole, what is the value of r? Kids, you have to understand. So let me just use this r as a different r, because using the same r actually confusing. Where is the eraser? There you are. Let me use a different r over here. Let's say I'm going to write this r as r h. I'm using h to represent radius of the horizontal circle. So in this case, r is the equal to radius. So if, when the object is going to be placed somewhere over here, you're going to have a circle that, let me use a different color, maybe red. You're going to have a circle of like this much. So maybe the radius over here is definitely slightly smaller than over here. So these radii of these vertical circles, which we showed in this example, so all of these circles, if over here, we draw the circles in all of these positions. These are the circles which is these are the circles that we are considering for this equation, because the object is going in horizontal circles. As the Earth is orbiting around its axis, try to understand, as the Earth is orbiting around its axis, energy that is placed over here is not going to rotate like this, it's going to rotate like that. ঠিক না? তাহলে আমাদের এই রেডিয়াসটা আস্তে আস্তে কমে আসবে কিনা? If you slowly move the
Yes,
object
sir.
from
Ji,
equatorial
sir.
location towards pole, this radius is slowly becoming less and less and less. So the more it becomes smaller, the less this force becomes, which means within this subtraction equation, this subtract t becomes less. So this result is slowly become larger and larger and larger. And how much large can it become? It can only become 100 Newton large, because exactly at the pole, the radius of this circular orbit becomes zero. This will be zero because at the pole it is just standing on a single point. It's not going around any circular motion whatsoever. So it's not losing any force to maintain circular motion, which means all the available 100 Newton force it can now exert onto the ground. So that's where the gravitational force comes in. Do you physically understand the significance of this whole thing? I could show you the mathematics involving trigonometry and everything right here, but I really don't want to do that because your syllabus doesn't cover that information to a very high detail value. It has some HCBC parts for certain question solving. Whenever those questions are going to show up in our past paper question papers or in our worksheet, I'm going to discuss about those parts. But for the time being, do you understand why the circular, the orbital motion is responsible for that thing?
Ji, sir.
angular velocity টাও কমে গেল।
Yeah, linear velocity কমে যাবে, but angular velocity same থাকবে. The further high we move from the equator towards the pole region, any of the polar region, I mean, I'm using the term high because I'm showing it to be moving from equator to our north pole. We could also go down towards the south pole. Doesn't matter. The further we move away from the equator towards any of the poles, the linear velocity of the object is going to become smaller because you're having a smaller orbit. So v equals to omega r. Your omega is a constant. Your r is becoming small. So obviously your v is going to become small. But your omega will also always remain the same because omega is given by which equation? 2 pi over t. 2 pi is a constant and t is the time period for that object. And that time period for any object placed on the surface of Earth is 24 hours. So omega is a constant for any object on the surface of Earth. Does that answer your question?
Yes, sir.
Beautiful. So that's that. What is the other thing that was left in the discussion? Oh, acha. Why? Acha. Between the positions, acha. Here's the deal. Let's say this is the Earth, North Pole, South Pole, and Earth is going around in anti-clockwise circle. What is the most likely convenient location on all of Earth's surface to launch a satellite from?
Sir, convenient বলতে কি location as in clear না কি ওরকম?
Which is gonna cause you to do least amount of work to place a satellite from the surface of the Earth to its orbit.
Equator,
Why?
because it will already have, like, it'll gain some, like, already have some velocity from the Earth. Because the Earth movement is already get the velocity that the highest amount of velocity. It's pole to zero, and like it increases to the equator.
That's a good response and a correct response. Anyone else? Do you have any other idea?
Shear talent সুন্দর, like gravitational force সুন্দর সহজ যাই কারণ
Yes, that's also another different reason, which Zarif just mentioned. I was actually looking for this response actually, that at the equator, the pull of the Earth is the weakest. So it is easy to get detached from that location, compared to any other location onto the pole. At the equator, the G is the smallest, so Earth is pulling it down by the least amount of force. So we have two advantages. If we have a satellite launch facility located on the equator, anywhere on the equator or close to equator, then we have two advantages. First advantage is that the object already has some significant kinetic energy. Now, if you wonder what kinetic energy has to do over here, what does it have to do over here? To give you a sense of the kinetic energy, let me tell you this part. Here's the thing that you need to understand. If we are trying to launch a satellite from the surface of a planet into an orbit, we have to make sure of a couple of things. First of all, we have to lift the object from any position of the surface of the planet to a certain distance away from the surface of the planet. So you have to give this object this amount of GP first. You have to make sure that the object is at far away distance, because you cannot have the satellite rotating around exactly on the terrain of the planet. That would be devastating or not purposeful for your requirement. So we have to first of all move the satellite a certain distance away from the surface, and that would require us to provide a minimum amount of GP towards the satellite. So you have to provide that energy towards that satellite using some rocket or whatever. The second thing is that to make sure that the satellite stays stable in the circular orbit, you have to set the satellite at a certain speed tangential to the circular orbit. So you have to provide this object a certain kinetic energy while it is in its orbit. So two things you have to understand. Maybe on the orbit, the object has zero energy. I'm considering it to be zero energy for the sake of simple understanding. Let's say on the surface of the planet, the object has zero energy. You have to move the object from the surface to a certain distance away from the surface. Let's say this amount of GP is, let's say, 1000 joule. So first of all, you have to provide the satellite 1000 joule. And then let's say to maintain this circular orbit, the amount of kinetic energy, because we have a V over here, we have an M over here, obviously there is a half mv square. The amount of kinetic energy that the object is going to require to go around in this circular orbit, let's say that is another 200 joule, let's say, which means you have to provide a minimum of 1200 joule to this satellite. 1000 joule to lift it up to the level that GP gain, and then 200 joule, additional 200 joule to serve the kinetic energy so that it can maintain its circular orbit. These are the two things that you have to provide. These are the minimum requirement that the satellite has to be located from the surface of Earth to its orbit. We actually can never do this with 1200 joule because the satellite cannot directly go there. We actually have to carry the satellite within a rocket, a propulsion engine. So the whole thing has to go over there and match the speed of the required satellite, then slowly leave the satellite in this place like a very tender release mechanism, and then the rocket has to slowly back up while the satellite is in its own orbit, and then the rocket has to retract back to Earth if it's a retractable rocket, like the way SpaceX does these days. So point is, we can never actually give exactly 1200 joule and expect the satellite to be located over there. We have to have other mechanisms involved in the process which spend a lot more than 1200 joule. But mathematically speaking, how much work needs to be done to place the satellite from the Earth's surface to its orbit? Mathematically speaking, is 1200 joule. 1000 joule for the example, for my example, 1000 joule for the GP gain, to 200 joule for the kinetic energy. The benefit of having a launch site located at the equator is that if you consider the mv square of this rocket, let's say the rocket is, in this case, is m, you want to state this in a certain circular orbit around the Earth, the mv square, half mv square, the kinetic energy of this rocket or satellite is the maximum for this location, because like I told you that you're gonna have different v's at different positions on the Earth. If you're at the equator at 0 degree latitude, you have the highest v, highest linear speed around the orbit on the surface because the radius is the largest. So if this, let's say at the pole, the actual kinetic energy of the whole rocket system is exactly 0 joule. Maybe right over here you have, because of the rotation of the Earth, maybe you have already 100 joule of kinetic energy available onto this object, which means if you want to set up a rocket, a satellite from this location into the orbit, you only have to provide it 1100 joule. Whereas if you want to launch the satellite from here and place it onto the orbit, you have to deliver it full 1200 joule. So choosing a location that is on an equator level, that is somewhere near the equator, actually helps to have some initially stored kinetic energy that we don't have to provide. So that's a significant gain, and the whole system can have to carry less fuel, so the whole process become more efficient in terms of fuel and achievable, and for many other factors I can use, but the idea is that we have to give the satellite less energy. That's benefit number one. And the second benefit is that compared here, the pull of the Earth is the strongest. Here the pull of the Earth is somewhat weak. So at this location, you are already significantly more far away from the center of the Earth compared to over here. So if you start from here, you have to overcome a much weaker gravitational field because the G value gravitational field strength over here is the weakest among all the places on the Earth. So your required energy to reach up to that level is also becoming small. All of these discussions that I'm doing, all these 2 points that I'm stating over here are actually stated under the basis of how much energy is required to transfer that satellite from a certain location on Earth to a certain location in the space. Because to make rocket propulsion successful, it is the energy that is very important. What does a rocket essentially do? It actually packs a huge amount of energy in a concentrated form. That's where the fuel comes in. Liquid fuels in the chemical bonds have concentrated energy. And then whenever we liberate those concentrated energy, then the chemical reaction makes it into heat, and then they expand because of the heat energy gases form, and then we drive that gas in a specific direction to the nose cone of the, not nose cone, the exhaust cone or the bell. There is called the bell of the rocket engine, and that actually causes them to go in a specific direction. And that's how we use Newton's third law and whole rocket propulsion works. So the idea is that to make the journey possible, you have to have a certain amount of energy storage in your vehicle, and you're going to slowly spend that energy to make your journey possible to that location. So the least amount of energy that you have to handle, the more payload or the more cargo or more luggage, more bigger satellite, more people, more food you can carry out in the outer space. So that's why choosing a least energetic option is always preferable. Does that make sense? Balwan?
Yes, sir.
এটা বুঝা গেছে কিনা? আচ্ছা, এরপরে আরেকটা জিনিস যেটা আছে সেটা হচ্ছে there are two things I'm going to derive. One is what we call escape velocity, and another one is the linear velocity for a satellite. Actually, linear velocity of satellite could be derived directly from here. Should I try it from here? Never mind. আমি দুটো আলাদা করে করতেছি।
একটা
বুঝি নাই।
স্যাটেলাইটের কাইনেটিক এনার্জি আছে না?
আবার বলো।
স্যাটেলাইটের তো মানে স্পিড আছে, তো এটাকে কাইনেটিক এনার্জি আছে না?
It is at its orbit.
জি স্যার।
Yeah, definitely. It has to continuously go around at a fixed velocity to maintain the circular orbit. Yes, it does have kinetic energy. Yes.
কাইনেটিক এনার্জিটা কোথায় থেকে পায়?
Oh, the rocket that brings the satellite to the orbit gives the satellite the kinetic energy. I mean, I want you to visualize it in this way. Let's say the rocket is Superman. So try to think of it. Or no, how can I? Let me just draw it. Let's say this is the rocket with wings and everything, and these are the bells from which the exhausts are coming up. The satellite is usually placed exactly in the top part over here. So what happens, the rocket actually goes into the aimed satellite's actual orbit. It goes there, it physically goes there and makes itself going around this orbit in a stable format. So it achieves that orbit along with the satellite. The satellite is within the rocket goes around the whole orbit in the same, because you have to understand that m does not matter. You see, the m really does not matter. So the rocket, being a heavy object, can still maintain that same orbit with the satellite within itself. So it goes around this orbit a couple of times. Typically that happens in the process of satellite launching, and the scientists from the ground station make sure that the orbit is okay and it is perfect, and we can now release the satellite. What the rocket typically does then it opens up its nose cone and exposes the satellite into the space, and it still keeps on moving. It is still moving in the same orbit. Then the rocket actually exhausts some nitrogen jets or some cold jet boosters in the reverse direction. When you have to understand, when the rocket is going around in this orbit, the engines are actually off. We don't have any exhaust happening. It's just moving around like a basic satellite. The rocket is now the whole satellite, and it has the actual satellite mechanism within itself. And when the rocket is about to release the satellite into the orbit, it just opens up its nose cone and release some reverse nitrogen jets, which slows down the rocket a little bit, and the satellite simply goes out by its own inertia out in the path. So the satellite keeps on rotating in the same speed, but the rocket slightly slows down in the same orbit. As the rocket slows down, it slowly falls behind and gets slightly closer to the Earth. That's how satellite geometry works. So the rocket falls down close to the Earth, and the satellite just starts floating on its own within that orbit. So basically, rocket does all the work. Rocket sets the satellite in its own orbit and then comes back to the Earth. Some satellites, in many cases, some satellites are also packed with some small amount of propulsion mechanism to make small corrections if there is any, because of some let's say solar flare happening, or some large meteorites or meteor getting pretty close by the Earth. So those those large scale cosmological events can actually give a little bit of uh, the little deviation from their original orbit. So many of the many are, I'm not sure, I mean, some, let's use the word some satellites can be equipped with some amount of small thruster mechanisms just in case they have to do some correction of their own. And that is usually always automated, so it is within the software. So if the satellite detects that no, I'm not in the same orbit, they can actually use their thrusters and immediately get back to the same orbit. But that's very insignificant, and that's a limited reserve for an infinite journey, because we want the satellite to give us data and be in the orbit for as long as possible. We're going to make the maximum value out of the product, but the amount of gas that you put within that jet thrusters is a limited resource. So these are not to be used for fun or just hula hopping. So yeah. আমি শুনতে পাচ্ছি না, আর একটু কাছে থেকে বলো।
স্যার রকেটটা কি আবার আর্থে চলে আসবে নাকি অরবিটে ঘুরতে থাকবে?
Oh, that depends upon how the people design the rocket. I mean, now currently the industry leader SpaceX has designed all of their rocket to be reusable. So all of their rockets now come back to the Earth. All of those. I think the boosters actually come back to that I know for a fact, and the top parts, I think, they also still come back. It depends upon the rocket design. If the rocket is designed to be reusable, now what if you wonder what is reusable? Reusable means that you set the satellite over at a pretty high above the atmosphere, and then the rocket has to make some re-entry through the atmosphere and eventually land on the Earth in one piece. That's reusability. So you have to design your rocket with extra parts and extra precautions so that it can actually withstand through the heating effect, thermal effect of the atmospheric friction, and then it can eventually land onto the ground in one piece. So if you can design all of these parts, then your rocket can be reusable. But if your rocket is not reusable, then you can only plan it to have a one-way journey. In that case, what happens is that the rocket simply goes up there, sets the satellite, and then simply slows down, and then the rocket just starts to fall within the Earth's atmosphere, and it is designed in such a way that as it is going to start to fall through the atmosphere, it's going to disintegrate into pieces, and it's basically going to vaporize it within the atmosphere. If it is not supposed to be reusable, it should not fall in chunks of pieces on the Earth's surface. If it is designed to be reusable, it should fall onto the Earth's surface softly in one piece. It depends upon the design of the rocket. বুঝতে পারছি?
Yes, sir.
Good. Oh, the next thing that I want to discuss is what do we mean by escape velocity. Okay, the idea of escape velocity is very simple. Let me show you this. Let's say this is a planet, maybe Earth. Planet sounds better, or Earth. Let's say this is a planet. I want to shoot an object from the surface of this planet such that this object is never going to come back to this planet. Now you have to understand this thing very well. Shooting an object away from a planet can be done at any velocity. You can throw a ball into the space towards the sky. You will soon find out that the ball is brought back to the ground. Why? The idea is very simple. Earth is continuously pulling it back. If you shoot the object with a certain amount of kinetic energy, I'm using the term energy over here, not force, because you all understand the idea of force pretty well up so far. Energy is the part that I want to use for this example. If you shoot the object with certain amount of kinetic energy, the object is going to slowly start to get upward, and is going to slowly keep on converting that kinetic energy into GP, and it's going to keep slowing down. The moment all of his kinetic energy is converted to GP, it has come to a zero velocity. But it is within a gravitational field. It cannot stay in this zero velocity because Earth is continuously pulling it back. So what's going to happen? It's going to start its journey back to the planet and convert its GP into K, and which is going to fall down onto the Earth once again. That's the basic stuff. So how can you achieve an object leaving a planet forever? I mean, you want to make sure that the object is never going to come back. This basically entails to give the object enough kinetic energy from the shooting point. Mark my words, hear them clearly and try to understand. This means to give the object enough kinetic energy right at the shooting point such that it would be able to cover infinite distance far away travel without coming to rest. It will definitely start to keep on slowing down. But that slowing down, if it would also be slowing down, because as it is getting farther away, it is slowing down more, but it is slowing down more slowly because the gravitational pull is becoming weaker because of the longer distance. So it is going to slow down slowly. So the rate of slowing down is going to be so slow that it's never going to become completely stationary, which means it can actually physically cover a journey of infinite distance. So that's the basic math that we take into account. So let's say this is the part over here. Let's say this is the infinite distance and this is the Earth surface. So if we want to make, this is the radius, this is the distance of radius of the planet. Let's say this is R, and so this is, let's say this is R, the radius, and let's say this distance is infinite distance, and we want to move an object of, let's say, M from here through here. So the amount of work done that we have to do, let's say delta GPE is gonna be delta phi M into delta phi. So I can write this as M multiplied by minus GM by infinite minus GM by R. বলবান এই এক্সপ্রেশনটা কি বুঝছো? এই ভ্যালু রিপ্লেসমেন্টটা কি বুঝা গেছে? এটা হচ্ছে ফাইনাল, এটা হচ্ছে ইনিশিয়াল, এই দুটো হচ্ছে পটেনশিয়ালের ভ্যালু। সো এখান থেকে আলটিমেটলি আমাদের এটা তো 0 হয়ে যাবে, এটা মাইনাস মাইনাসে প্লাস হয়ে যাবে, আলটিমেটলি আমরা পাবো কি GMM by R. This is the amount of GP that you have to provide the object to make this journey possible. Ideally, we can provide this energy in terms of kinetic energy. So if the object had an initial kinetic energy of, let's say, half m v squared, and m and m cancels each other out, so you can see that. And then if we subject v from here, this is what we call the escape velocity. This would be given by root over of 2gm by R. This is what we call the escape velocity for applicable for a certain planet. So it is dependent on basically two factors. One is how much is massive is that planet, and how far did the object start. I mean, this R basically in this case represents the surface, because the idea of escape velocity goes like this, that the amount of energy, the amount of minimum speed or minimum velocity we have to shoot an object vertically away from the surface of the object, so that it will never come back to the object. It will never come back to the surface, to the planet ever. So the idea of escape velocity is coined upon the term that it would be shot from the surface itself. So R in this case basically represents the radius of the planet, or in other terms, it represents the distance of the object from the center of the planet. So this is the expression for escape velocity. It simply means that if we shoot an object at this speed from Earth, from any planet, this object is not going to come back in an isolated space. Isolated space means we only have this planet and nothing in, we only have this planet and this mass over here and nothing else around. In an isolated space, this object M should be able to cover infinite amount of distance journey with the energy that we initially gave it to begin with. The other mathematical expression, the last mathematical expression to this class, is going to be applicable for orbital speed for a satellite, which I could pick up a bit earlier, but I actually drifted down to other relevant discussions. So orbital velocity. of say আমি তো মাউস দিয়ে ভালোই লিখতে পারি, অ্যাটলিস্ট লেখাগুলোকে ইংলিশ হিসেবে বোঝা যাচ্ছে, তাই না? Orbital velocity of a satellite. This is pretty simple to do. We're gonna start with the very same expression of this one. I always prefer to start with this equation. The only difference that is gonna be is because we want to find out the orbital speed v. I'm gonna write the fc in terms of v, and I'm gonna use the same expression rs other than writing the whole r plus h. So rs would be the radial orbital radius of the satellite. So I'm gonna use that term. So if I go over there, so fc equals to no. Sorry. So fc equals to fg. So I can write fc as m b square divided by rs. This is the radius of the satellite, orbital radius, equals to g m divided by rs squared. M and m crosses out, rs and square crosses out. So what we have is v square equals to gm by r of the satellite. So orbital speed is given by root over of gm by r. I could write the s. Let me write the s. What is important that you should not confuse between these two expressions. Have a look. Escape velocity is given by what? Root over of 2gm by r. Orbital velocity is given by what? Root over of gm by r. What is the difference? 1, 2. There is a difference of 2 over here. So you should not mess up these two expressions. This is really important. You should not confuse these expressions. Escape velocity is the term that we need to shoot it at a minimum speed, the minimum speed at which our object must be shot so that it doesn't come back to us, the planet. Whereas orbital velocity is orbital velocity. দুটো এক্সপ্রেশনের বেসিক টার্ম শেপ সেম, root over of gm by r. And also if we find out the fundamental unit of this quantity, we're still gonna get meter per second and meter per second for both of them. You can check this out at your own time, no big deal, be my guest. And if you get something else other than meter per second, please let me know. I'll have a look at it. But you should not mess up these two expressions. For the sake of convenience, I'm going to show you right now that what formula are we going to have available in your actual what? Oh, what are you gonna have in your actual do I have past year question papers over here? Any past year question papers over here? I don't. Might as well download some. Do we have any past year question papers over here? Documents. Open past year question papers. Separate have this is one of the folder, nothing in the new folder. আচ্ছা, নরমাল একটা past year question paper ডাউনলোড করেই দেখাই। আচ্ছা, এই আম্মু কল করছিলেন, আমাকে কল ব্যাক করতে হবে। ফারহানের আম্মু কি বুঝতেছি জানো, জিসি গাইড না তোমাদের কোশ্চেন কই পাওয়া যায়?
পাপা কেমব্রিজে দেখেন।
পাপা কেমব্রিজে পাওয়া সহজ। পাপা কেমব্রিজ 9702 any year. Land in May, June, no. Oof. Okay. KP41, KP41. View. দিলে তো ডাউনলোডে চলে আসলো। আচ্ছা ঠিক আছে, ডাউনলোড করার প্রবলেম নাই, এখান থেকে দেখি। সো এখানে এটা ডাউনলোড করলাম হচ্ছে তোমাদের দেখানোর জন্য যে তোমাদের ফর্মুলা শিটে কি কি ফর্মুলা থাকবে সেটা দেখানোর জন্য। সো what formulas are you gonna have? Are you gonna have the value of escape velocity or anything like that? So if you have a look right over here, x equals to q plus half a square, b square equals to square plus twice s, work done on a gas w equals to p rho v, gravitational potential minus gm by r, hydrostatic pressure p equals to rho gh. এগুলা হচ্ছে থার্মাল চ্যাপ্টার, সিম্পল হার্মোনিক মোশন চ্যাপ্টার, এগুলা ডপলার এফেক্ট, electric potential, capacitor, rigidity, current, Hall voltage, rigidity constant. Now, you are not going to have any of the expression for whether for any of these two expressions. So you have to remember them by your own memory if you want to skip the derivation for a math. So escape velocity is equal to 2 gm by r, whereas orbital velocity is equal to gm by r. Should not mess up these two expressions. Some student, not all of them, some students tend to mess up these two expressions. I mean, they write the escape velocity expression in the orbital velocity and vice versa. Just be careful about it. That's all I'm asking. I don't intend to teach any more today, but if you have any question up so far of this lecture, please shoot. Anyone? আচ্ছা, আমাদের এরপরে ক্লাস হচ্ছে বুধবার। কটার সময় ছিল যেন? চেঞ্জ করে আমরা বৃহস্পতিবার ক্লাস সরাই বুধবার এনে কটার সময় দিয়েছিলাম মনে আছে কারো? লেখা রাখতে ভুলে গেছি। হ্যালো,
স্যার একটা থেকে
ছিল?
একটা থেকে তিনটা।
আচ্ছা শোনো, আমি অ্যাকচুয়ালি এটা ভুলে গেছি। তোমরা এটা একটু আমাদের মেসেঞ্জার গ্রুপে একটু প্লিজ কনফার্ম করে আমাকে, আমি পরে ওখান থেকে দেখে নিব। এখন এটা নিয়ে বদার করতে যাচ্ছি না যে আইদার একটা থেকে দুপুরে ছিল, এটা আমি শিওর, আইদার একটা থেকে ছিল অথবা দুইটা থেকে ছিল। কয়টা থেকে এটা আমি ভুলে গেছি। একটু আমাকে সবাই একটু আলাপ করে আমাকে একটু জানাই।
ওয়েডনেসডেতে একটা থেকে তিনটা ছিল।
আচ্ছা ঠিক আছে, একটা থেকে তিনটা ছিল, ফাইন। ওকে, থ্যাংক ইউ, আল্লাহ হাফেজ। আমি একটু বলে চাপ করে দিচ্ছি, দরকার মতো দেখে নিও। ফিমানিল্লাহ।
আল্লাহ হাফেজ স্যার।